All right, so class 1, we're going to talk about some mathematical models and some algebraic expressions. Algebraic expressions and real numbers, I've left for you to do self-review. That's prerequisite material. So you need to read about that in the textbook if you don't remember it from a previous class. There's just a teeny bit of it in this lecture. All right, so mathematical models. A common thing we hear when we're teaching math is, when are we ever going to need to use this? Right? I hear this all the time. And the answer is right now. So let's take a look at this bar graph showing the average cost of tuition and fees at public 4-year U.S. colleges, adjusted for inflation, from 2000 to 2010. So again, this is adjusted for inflation. So these are increasing above and beyond inflation. So I want you to analyze this graph, discuss it in your groups, write down a few observations about the data. What conclusions can you draw from this graph? Okay, what are a few observations that you came up with? Okay, that is a really good observation. But what? But people don't make more money, right? So it's growing faster than inflation. Or we should say growing faster than income, right? Because income basically grows with inflation. These prices are growing past inflation because these have already been adjusted. Yeah. Yeah. Big jump. 03 to 04. I wonder what could have caused that. There was something. The recession started like in 07. And 09 to 10. That's true. Yeah. I mean, around 02 we start seeing it spike up a bit more, but before yeah, so those are some good observations. Do you know what this little symbol means here? Anybody seen that before? Yeah, because we're starting at $3,000 and each tick mark now is 400. So there's a lot of space missing here to get down to 0. So rather than show it all, you put that little mark there to indicate I'm leaving a bunch of numbers out here. So that's what that means. If you ever have to make a graph and you jump to a big number, you put that little symbol. So it means skipped a big chunk. So as a student in public higher education, as all of you are, what questions about the average cost of tuition and fees at public 4-year colleges might you be interested in asking? Okay. What does my money pay for? What else? Yes. Right. Why is the price increasing so much? Yes. Is financial aid also increasing? And that's an interesting question because a lot of people actually blame the rising prices on increasing financial aid. They say, we're giving out more financial aid, which means colleges know that they can charge more money. Who knows, chicken or the egg, right? Right, right. Any other questions you'd want to know? Okay. So the good news is that it may be possible to answer these questions using mathematics. Okay, so we can work with the real data collected, presented in the bar graph, to find a mathematical model, or simply a model. And a model is a mathematical representation, like an equation or a formula, of a real-world situation. It can describe the relationship between two or more quantities. We can write an equation relating them. So this is an important step in the problem-solving process, being able to convert a description of a relationship to an equation. Okay, so let's use some mathematics to answer some questions about the cost of tuition and fees using a model of the data presented above. Okay. So we actually have come up with a formula, but we used some mathematics that you don't know how to do yet, but the book did for us. Use some mathematics to take that data and write a formula that tells us T, the cost of tuition and fees, in year X, and we're measuring X in years since the year 2000. So I want to use this formula to find the average cost of tuition for the college year ending in 2010. So they've given me 2010. Is that an X or a T? X, because X is representing years, right? Now what number should I plug in for X? 10, because we're measuring in years after 2000. So 2010 is 10 years after 2000. So I'm going to plug a 10 in here. T equals 4 times 10 squared plus 341 times 10 plus 3194. So that's, pull up a calculator. Okay, so 4 times 10 squared plus 341 times 10 plus 3194, $7,004 tuition in 2010 based on the model. So that's what the model predicts for 2010. We have a mathematical model. It's just an invention by humans meant to help us make predictions. So let's go back and see what the actual tuition was in 2010 based on this graph. What was it? 7,020. So that's a really good estimate. We're only off by $16. So this is an underestimate because it's a little lower than the actual, but it's close. So now I want to use the model, that is my formula, to predict the average cost of tuition and fees in the year 2014 and in the year 2050. So I'll pull up my calculator again, and I want to plug in a 14 this time for the year 2014. Just changing my 10s to 14s here. And I get 8,752. And for 2050, I want to plug in 50s for my x's. 50. $30,244. Not excited about paying for kids to go to college. Okay, so does the prediction for the year 2050 seem plausible? Why not? You think we broke the function? So the function is, it's not giving me a good prediction. 2050 is too far away from the data that we're looking at to be able to use it accurately. Yeah. Okay, so that's good. So we're thinking no, 2050 is too far away. Data from 2000 to 2010 is way far away from 2050. The trend could change, right? And it seems like many people are predicting will. There are many economists out there saying that higher education is the next big bubble to burst, and they just can't keep raising prices the way that they are, or people will stop going. I think both. Yeah. I don't know. I mean, Harvard may always be able to charge whatever they want, but so sometimes a model, if you extend too far beyond the present data, can lead to an estimate that just doesn't make sense or is unreasonable. In these situations, we say that a model breakdown has occurred. So that's just a little introduction to modeling. If you keep your ears out, you'll hear people mention models. They don't explain that they're using math, but they'll say, oh, our model about climate change, or our model about the way we figure out how many people are at a large event, right? They use the word model. They don't explain that that is math. Right? Keep your ears out. You'll hear people use the word model all the time. All right, so if we move on to the next topic here, it's sets. So a set is just a collection of objects. For example, we could have the set of students in this class, the set of large species of cats, or the set of Oscar winners for Best Actress. The objects in a set are called the elements of the set. We can write a set by just listing its elements between curly brackets. Okay, so this form of set representation is called the roster method. Just write out a roster of everything in the set. So for example, we could let set A represent the set of the Three Stooges. So we would write out A equals, so the set A is, and then you put curly brackets, and you list out the members of the Three Stooges, Larry, Moe, and Curly. So in the roster method, you use commas to separate the elements of the set. All right, so if B represents the set of the 7 dwarves, then B equals curly brackets. Let's use the roster method to list them. Who are the 7 dwarves? Sleepy, Dopey, Sneezy, Grumpy. I heard somebody say Doc. Ashful, yeah. That's 1, 2, 3, 4, 5, 6. Happy. Roster method. Curly brackets, just list them all out. All right, the sets we encounter in this class, though, are not typically going to be sets of things like the 7 dwarves. They're going to be sets of numbers. So there are some other ways to write sets of numbers that are going to be more efficient than just listing every number in the set. Sometimes it could be a really big set. So the first one is called set builder notation. It's a descriptive way to write a set. Generally speaking, it looks like curly bracket, X, and then a vertical line, and then some conditions. The vertical line is read such that. So this you would read as the set of all X's such that X meets some condition. Do a couple examples, it'll be a little clearer. So for example, if I write curly bracket X, vertical line, X less than 0, you would read this as the set of all X's such that X is less than 0. What numbers am I describing? Negative numbers. So this is just a fancy set builder notation way of saying the negative numbers. The set of all X's such that X is less than 0. All right, and then we can talk about union and intersection of sets. So here's a little example to help you remember what union means. So the members of the 1961 rock band, the Beatles, that performed in Hamburg, Germany, was not the same foursome that arrived in the US in 1964. So if we let A represent the members of the 1961 Beatles, so A is going to be a set of 4 people, and B is going to represent the members of the 1964 group, another set of different 4 people. We use the roster method to list the elements of each set. So set A is John Lennon, Paul McCartney, George Harrison, Stewart, Sutcliffe, and Pete Best. So there were actually 5 of them. 2, 3, 4, 5, yeah. And then set B, the Beatles as they were when they arrived in the United States, is John Lennon, Paul McCartney, George Harrison, and Ringo Starr. So now imagine that all the members listed above are still alive and we're going to plan a reunion. List the members who would come to the reunion and label it set C. All of them, yeah. So we would just write them out. I'm going to put initials to save myself a little time here. All of them would come to the reunion. So when you union 2 sets, think of it as a reunion. Everybody comes. But you don't have to list John Lennon twice, right? He's there. You don't have to put him in the curly brackets twice. So the way we denote a union is with a big U. So if I wanted to put the union of sets A and B, you write A union B. So take 30 seconds, write down in your own words what it means to form the union of 2 sets, based on the example we just did. All right, now we're going to let D be a new set, and it represents the set made up of members of both bands. Guys who are in both bands, the original and the 1964 version. Nope, only people who were in both. Who was in both? John Lennon, Paul McCartney, George Harrison. So D represents the intersection of sets A and B. And you can think of intersection like with a road, right? An intersection is where 2 roads overlap, where they cross. So an intersection of 2 sets is where 2 sets overlap, what they have in common. So you can put in your own words, how do you find the intersection of 2 sets? Take 30 seconds to do that. A Venn diagram is a nice way, visual way, to help us represent the union and intersection of 2 sets. So if I draw one circle to represent 1961 Beatles, and another circle to represent 1964 Beatles, what members of the bands belong in the middle, where the 2 circles overlap? The intersection. We would have John Lennon, Paul McCartney, George Harrison. And then what members were just in 1961? Yeah, Stewart something and Pete Best. And then what member was strictly in 1964? Ringo Starr. So it's just a nice visual way to show the union and the intersection. So the union is just everybody listed anywhere. The intersection are the guys in the overlap.
Wait, so in 1961, though, wouldn't you put all of that?
Yeah, so...
No, I see what you mean, but like, just, oh, who are just in 1961.
Yes, right. So if you, I should have done like 2 circles, different colors maybe. That would make it clearer. So you can see that John Lennon, Paul McCartney, and George Harrison are in the 1964 circle, and they're in the 1961 circle. Does that make sense? Okay. So they're technically inside both circles. Yeah. Okay, so topic number 3, moving on from sets, is absolute value. So we have an algebraic definition of absolute value that says the absolute value of x is x when x is positive. So if x is already positive and you take its absolute value, it just stays positive. Right? So if x is bigger than 0, that means that x is positive. Take its absolute value, just stays the same. But if x is negative, if x is less than 0, then the absolute value of x is what? It's still positive, but why is there a negative sign there? Yes, that is very true. Why does this definition have a negative sign in front of it? Yes, yeah, we're on the right track. Yeah, because x is already negative, and if we put a negative sign in front of it, it says negative, negative, whatever. And what's the opposite of a negative? Positive. So this is like saying the absolute value of 5 is 5, right? Because I'm positive, so it just stays the number. The absolute value of negative 5 is the opposite of negative 5, right? I've got this negative sign is this, and this negative sign came from the negative 5. And negative negative 5 is 5. Yeah, absolute value just makes stuff positive. Yeah. So this is the sort of fancy mathematical notation, how we define it. It is much simpler to say it just makes it positive. But just trying to help you translate why it's written this way. Yep. Yep, that's a good way to think of it too, because distance is always positive. All right, so we just talked about that. All right, so I would like you to discuss in your groups. You have a couple of 3 statements about absolute value. I want you to write whether each statement is always true, sometimes true, or never true. And if it's sometimes or never true, either change it so that it's always true or show a counterexample, how you know it's not true. The absolute value, the negative of an absolute value has to be negative, right? So if you put the negative outside, so for example, the negative absolute value of 5, right? Well, you do the absolute value first. The absolute value of 5 is 5, so this says negative 5. Right? Or we could put a negative outside and put a negative 3 inside, right? The absolute value of negative 3 is still 3, but we still have the negative outside, so we end up with negative 3. So it's always going to come out negative, no matter what we put in there. Except what? When is it not negative? 0. Yeah. Sometimes. There's one time when it's not. If I put a negative outside and the absolute value of 0 is 0, which is not technically negative. Correct. It is neither negative nor positive. Nope, because 0 isn't negative. It only takes one time. Okay, you could do that. It is always true except for 0. You can write that if you want. Yeah, I know. How about the absolute value of the opposite of x? Is that negative?
No.
Is it ever negative? No. So this is never. It's either going to be positive or 0, right? So pick a number. We could put in the absolute value of the opposite of 5, and we would get 5, right? You're pretty much always going to get a positive, or in one case, you could get 0. All right, how about a minus b equals b minus a? Always, sometimes, never. Always. So if we pick some examples just to try it out, we could do the absolute value of 5 minus 3. And we want to know, does that equal the absolute value of 3 minus 5? Well, on the left, we get positive 2. And on the right, we get negative 2. But both sides are an absolute value, which means both sides are 2 and they are equal. So I can't think of any two numbers that where this won't happen, right? Does it work with negatives? Like what if I do -3 minus -2? Does that equal -2 minus -3? So minus a negative, that's adding, right? So -3 plus 2 is -1. And -2 plus 3 is +1. So yep, still works. 1 equals 1. All right, so it seems like this is going to be always. All right, that is great. We are a couple minutes over time, so we're going to skip the group activity. I just want to point out that on the page after that, your homework is listed. So there's a My Math Lab assignment and some reading that I'd like you to do.